Welcome back. Now that we've talked about what double integrals do, we're going to look at evaluating a double integral. So we have this theorem, Fubini's theorem, and this is the first form. We have a more specific form later. But if we have a multivariate function, which is continuous on a rectangular region, so my x values span from A to B, and my y values go from C to D. We can say that this double integral over that rectangular region of the function integrated with respect to the area, so both the x and y variable, can be written two ways. So we can say the integral from A to B, and then we have this outer region. When we talk about y, we use C and D to represent that range. So in this first situation, we would integrate with respect to x first, evaluate it along those x bounds, or the x bounds of my rectangular region, then we would integrate with respect to y. Doesn't mean we have to do it that way. We could also integrate with respect to y, and you'll notice then I have C and D on my inner, I should say, integral symbol. So then A to B, that's with respect to dx. The order doesn't matter. We can go dx dy or dy dx. It's just a matter of which is more convenient. So depending on our bounds, we could have a situation maybe where the bounds looked like this. And if we were integrating horizontally, then we would have a different left and right. So it might make more sense to go above and below, up and down. Okay, so we'll talk about that, and we'll talk about choosing which way makes sense as we move further through this chapter. But right here, because we're dealing with rectangular region R, so my x is defined from A and B, and my y is defined from C and D. As long as it's rectangular, this is going to be very easy for us to evaluate. So just refreshing some vocabulary, double integrals over rectangles, we can call those iterated integrals. Thus, that means we can evaluate a double integral by integrating with one variable at a time using our fundamental theorem of calculus. And we can use either order, and this is out of genuine convenience. So you're going to draw your region and think about what order you should use. Let's look at an example. So here, we're going to evaluate a multivariate function over a rectangular region. The function is the square root of 1 minus x squared. And my rectangular region, of course, you're always going to want to be sketching these regions, but my region here, we've got 1 and -1 on the x-axis, +2 and -2 on the y-axis. So this is the rectangular region in the xy plane that we are mapping up to our surface F. So we've got this surface, and we want to find the volume between that surface and this rectangular region. That's what we're doing. So we're finding the double integral over that region R, rectangular region, of 1 minus x squared dA. So as I said, there might be situations where your left and right or your upper and lower bounds are defined by 2 or even 3 different functions, and we need to break it into pieces. In this case, the order really doesn't matter if we do y first versus x. Either one is going to give us a solution. All right, so what is the surface that we are dealing with here, right? Let's just think about what that surface is. My function f of xy, we can call that z. Z equals the square root of 1 minus x squared, or rather z squared equals 1 minus x squared. or x squared plus z squared equals 1. Now, we always want to think about the graph of our surface and the region, because that's going to help us know, what we are looking at. So here's my XYZ plane. And this is actually a cylinder. It's a cylinder. Since y is missing, it's traveling around the y-axis, and because that square root was there, it's actually only the top half of the cylinder. So we've got some circular cylinder, which looks roughly like this along your y-axis. Okay, so here's my circular cylinder, the top half of the cylinder, and this is actually a geometric shape. So if we think about that region, right, where my x's are between +1 and -1, that's right here on these edges, and my y values are between -2 and 2, this region is really just the volume of this piece of a cylinder. Of course, since this is a geometric shape, we can find the volume. It's going to be the volume of a cylinder is the area of the base, and this is a circular cylinder of radius 1, pi r squared times the height. And since it's only half of the cylinder, we'll put that in there. So the radius on this cylinder, that radius is from the center out is 1. So we're going to plug a 1 in there. And the height of my cylinder, thinking about this rectangular region, that height is 4. So my volume is 1/2 pi times 1 squared times 4. We get 2 pi. 2 pi is going to be the solution for this twice integrated integral, right? That's the volume between this cylinder and that rectangular region down on the xy plane. Now, if you can use geometry to solve the integral, why not use geometry? It's just most of the time we don't have that geometry there. So I show you this example, one, because I want you to understand the setup, but two, know that you have these shortcut methods that are perfectly acceptable to use as long as you are showing your work. Now, if we were to actually set this up, my first integral, I'm going to say my bounds go from -1 to +1. So x equals -1 to x equals +1. My second integral, then my y goes from -2 to +2. So we've got -2 on the bottom of that region, +2 on the top of that region. And we would need to integrate 1 minus x squared. That would be to the 1/2 power, and then I would write my order of integration by saying dy and then dx. So this gives us a problem here on the inside that we need to calculate. Once we calculate the inner integral, then we would just basically be repeating this process a second time. Now, if I'm integrating this with respect to y, I don't have a y here, which means we treat that as a constant. I'll be left with x equals -1 to x equals 1. This is going to be y times 1 minus x squared to the 1/2. We evaluate that from 2 to -2, and then we've got our dx. So simplifying this, I'm going to say -1 to 1. I have 2, 1 minus x squared to the 1/2 minus -2, 1 minus x squared to the 1/2. And so minus that -2, that's a +2, or we will just have a 4. So I've got a 4 here. And now we just need to integrate with respect to x. One thing I encourage for you to do, and I didn't do that here, but write what these variables are equal to. We've got y equal to +2, y equal to -2. These values represent a y. We were integrating with respect to y. So it's easy to get confused and to plug those in for x. So now as we continue working through this, that 4 can come out in front, and this one really isn't a nice integral to integrate. I have 4 integral -1 to 1 minus x squared to the 1/2 dx. And this piece right here, this isn't very fun for us to integrate. We actually have to use trig identities and substitutions, a u substitution. I don't want to deal with that. I'm just going to ask you to trust me and know that we're going to get pi over 2. We still have that 4 in front. So the solution for this integral would be 2 pi. And I hope you can obviously see that the geometry in this situation made our life a little bit easier, okay? The point of this was to just let you know how to set these integrals up. So one other thing, I could have said dx, dy, and that would have just changed the order in which I wrote these bounds on my integration. If I had dx first, then these would be x goes from -1 to +1, and then dy, those would have my y's on the outer integral symbol. All right, so that's it for this video. I'm going to do another one where we actually solve one that's more manageable.